Hi everyone. Our algorithms final group project is going to be on magic square puzzles. We're going to be talking about what magic squares are. We're going to analyze what existing algorithms solve magic squares and some of the unique algorithms we tried to come up with um, to solve both a magic square from scratch and a partially filled magic square.
My name is Suno. I'm going to introduce what makes magic squares. A magic square is a matrix of numbers that has special properties. The first property of a magic square is that the matrix is a square of size n by n and consists of integers from the set containing all the numbers from 1 to n squared. The second main property is that each number from this set occurs once with no repetition, and each number from the set is included. The third main property of a magic square is that all columns and rows will add to the same number, which is the magic constant. And this constant can be calculated by n times n squared plus 1 and divided by 2. A matrix satisfying these three properties makes a magic square. Here is an example of a magic square of size n equals to 3, which is a 3 by 3 matrix, and it contains the full set of numbers from 1 to 9 without repetition. We can use the formula to calculate the magic constant, and here is to be 15.
Hello, my name is Maxwell Vogel, and I'm going to cover some existing algorithm analysis for magic squares. Some popular existing algorithms work by filling in the magic square matrix programmatically, where every single element that is filled in will result in a valid magic square at the end of the algorithm. There's different types of algorithms that are used for even and odd numbered side lengths. In our analysis, we're primarily focusing on odd numbered side lengths. It's impossible to make a magic square of size less than n equals 3, so the minimum side length needs to be n equals 3. Additionally, there's also many algorithms that have the additional requirement that the diagonals add up to the magic constant. In our analysis, we are ignoring this requirement. So an example of one of these algorithms is that you start with the number 1 and you fill in its location in n over 2, n minus 1 using 0 indexing. Then you programmatically fill in the rest of the numbers up to n squared by following a certain set of rules. Every single time you change the row and column according to a specific rule. And additionally, you follow guidelines that if there's an existing spot already filled in or the next row or column is off the grid, you jump around to a different part of the grid. And you continue this until all spots are filled. A result of this can show n equals 3 and n equals 5 here, but we're going to primarily focus on the n equals 5, as this will show some more insights into the algorithm. The first insight is that the numbers are filled in sequentially when possible from the lower left to upper right-hand corner. In this case, you can see that there's several different instances where consecutive numbers will be located on a diagonal from each other. Additionally, the numbers from the set 1, 2, 3, 4, and 5, or 1 to n, they all do not share a row or column with each other. And then additional things is that different squares can be created through a change in the first number position and placement rules. So for example, if you use a different diagonal direction from top right to lower left, you'll get a mirrored version of this magic square. Another analysis that you can do when looking into magic squares is to determine what are all the different subsets of numbers that you can use to create a specific magic square. Starting with n equals 3, we can see on the right-hand side that there's 6 different subsets that can be used to add up to the magic constant of 15. There are additional subsets that add up to c equals 15, such as 4, 5, and 6, and 2, 5, and 8. But these cannot be used as this will create an unsolvable puzzle, as there's not enough other subsets to create the magic square. And one major takeaway from this is that every number is used in 2 different subsets for creating magic squares. Increasing the size to n equals 5, we can see that there's over 600 different possible subsets, and scaling to n equals 7, there's just under 6,000 different subsets. While not all of these are viable, as it will block some solution subsets from being used, we can see that this number starts to scale dramatically. And an analysis into this can find that finding different subsets for the magic square problem is a variation of a subset sum problem, which is NP complete. Therefore, the magic subsets reduces to a subset sum problem the magic subsets, therefore, is an NP-complete problem.
Hi, I'm Neil, and I'll be talking about one approach to solve for a magic square using a brute force algorithm with recursion. For the algorithm example, we're going to be using a 3x3 magic square. The first step is to permutate the empty cells in the first row and then check if the sum of the row equals the magic constant, which is 15 in the case of a 3x3 magic square. If the sum of the first row does not equal the magic constant, the algorithm backtracks and permutates the first row until the sum of the row does equal the magic constant. This step is repeated for the second and third rows until the sum of all rows equal the magic constant. This helps to save a lot of time because there's no useless permutations in the second and third row until we know for certain that the first row has a sum that is equal to the magic constant. Once all the rows have been permutated and the row sums have been checked, the algorithm then checks the column sums. If the column sums does not equal 15 or the magic constant, the permutation steps are repeated without changing the sum of the rows until the sum of the columns equal the magic constant. This way, we then have a magic square with all the row sums and column sums equaling the magic constant. The time concurrency of this algorithm would be n square, where n is the number of elements in a magic square. So for a 3x3 magic square, n would equal 9. Since backtracking and recursion is considered, the algorithm works well for a smaller n value, but it's clear that a pure brute force approach such as this is really inefficient for squares of higher orders, since the number of possible arrangements rises very rapidly.
My name is Suno. I'm going to continue with brute force method 2 without recursion. So the simplest way to solve a magic square is to use brute force, but it is very time consuming. As mentioned above, the magic constant is calculated to be 15 for 3x3 magic squares. First, we want to get all the permutations of numbers from 1 to 9, then position all these numbers of each permutation into 9 spaces of the square, and test through all the squares and label the ones whose sum of each column and row is 15. All these labeled squares are solvable magic squares, and this is an exhaustive search for generating all magic squares of order 3. The algorithm will have a 9 nested loops since there are 9 spaces for a 3x3 magic square. The loops will check all the numbers from 1 to 9 for each space, which means it will run 9 to the power of 9 times to get the results. And to get the results for a 5x5 square, it will take 25 to the power of 25 times to run the functions. We might have destroyed the Earth along with the computer that was running this algorithm back then. The problem is that it takes a lot of time to check the square with duplicates, but we don't want any duplicates. Therefore, we can use backtracking technology to skip over all the permutations with duplicates. And by skipping over these permutations, the algorithm will be more efficient.
Hi, I'm Sadak, and I'll be going through the dynamic programming algorithm. And as you can see, I'll be building on what my colleague Max has already talked about, especially about the existing algorithm analysis. And the algorithm basically goes through the matrix diagonal by diagonal. And its main advantage for us is that it can produce multiple and many varied, if for our analysis varied enough, matrices and magic squares, enough to cover use cases for a certain input. And as you can see, we can vary the matrices depending on where we place the first number and where we place and the placements of the subsequent 4 numbers. As you can see, they're here marked in red. And the dynamic programming algorithm itself is just a method to both fill a matrix and verify that a given input can be turned into a valid magic squares. Well, as said before, we added the numbers in increments of 1, each at a higher row and column positions. And we notice that we do get around a major constraint. We do not repeat numbers, and the sequence produced in turn reproduces the sum needed, assuming the, well, it's a major assumption here that the numbers are consecutive. If the input is already given, the algorithm notes the number and it skips it when the turn comes up. A major limitation of this algorithm is that it theoretically cannot reproduce all 5x5 squares. That is a very large number, and it is, as said before in Max's analysis, is that it is somewhat outside the scope of this project. But only but the immediate verifiable subset of those matrices is good enough for our purposes, for the purposes of verifying inputs that have already been given. And the algorithm runs in n-squared time. It was written here as n by n, just to emphasize that we will be doing one check for each position in the n by n matrix. So it is one operation for each availability, and there are n-squared positions. And here you could see in a 3x3 matrix the process. So here the diagonal goes left. So first we actually went up and then went down, and then after that you can add an increment of 2 after 5. So by the way, all 3x3 matrices have to have 5 at the center. It's just how they work. And lesson learned, the conclusion, well, this project has been a great teaching experience and a valuable foray into the real world of problem solving in computer science. It was, we started with a very simple problem, with a very simple premise of a problem, and we stumbled upon what turned out to be an NP-complete problem. And we only really knew that after we studied module 12, and we came across the analysis of NP-complete and NP-hard problems and so on. It was a very enlightening, very empowering experience. And about our algorithm, the algorithms themselves, they are, by their nature, by the nature of the problem, limited. Our brute force algorithm is not practical for sizes above 3x3, and our dynamic programming algorithm produces a very large but still incomplete subset of all magic squares of matrices 5x5 and beyond. As said above, our goal is not to reproduce all of them. That is pretty difficult. We simply want a method or a practical game solving mechanism for anybody who just enjoys filling in 3x3 or 5x5 magic matrices in the same way that somebody would fill in, let's say, a Sudoku problem. As said, all of this works well for the scope defined in this project, but any further progress will have us tackle the problem of NP completeness itself. And the way things are, NP completeness will be with us for the rest of our careers as computer scientists. I mean, this is just a start here, and it was wonderful to get to experience this firsthand without training wheels, so to say. And yeah, hopefully you enjoyed this project as much as we have. And all right.